Hi. Today I'm going to present moving target defense for embedded deep visual sensing against adversarial examples. I'm Song Chun from Nanyang Technological University, and the collaborators of this work are Zheng Yu and Ray. A brief background. Deep learning has been used in increasing number of applications, including automotive, healthcare system, and consumer electronics. However, research has shown that deep learning applications are vulnerable to adversarial example attack, which are crafted inputs aiming to mislead deep models while remains unnoticeable to human eyes. And such attack is an immediate concern because it can be launched in real world. For example, existing studies show that by putting some paper stickers at the scheduled positions on a stop sign, it can mislead the road sign classifier to think it is a speed limit sign. And moreover, a recent research done by the Kin Security Lab showed that by putting some sticker on road, it managed to fool the deep learning-based lane detectors and leading to great danger. The construction of adversarial examples can be formulated to a constraint optimization problem. And the goal is to minimize the distance between the original samples and the adversarial examples, subject to that the output of the neural network is different from the correct label. And according to the attacker's goal, targeted attack aims to misclassify an input to a specific target class, and non-targeted attacks aims to misclassify the input to any class other than the correct one. And according to the attacker's knowledge, black box attack requires only limited or no knowledge of the model internals while constructing adversarial examples. And white box attacks require full or lots of knowledge of the model's internals. And currently, there are mainly two streams of defenses against adversarial example. The first one is called model hardening, that modifies the neural network itself. And adversarial training is one of the model hardening approach. It includes adversarial example during the model training stage, using its correct labels. However, it only results in robustness against the used adversarial example during the training stage. And gradient masking is another model hardening approach. It aims to make the gradients that is useful for constructing adversarial example non-existent or incorrect. However, this is a kind of incomplete defense in the sense that it only increased the difficulty for the attacker to solve the constraint optimization problem. However, it doesn't mean the problem has no solution. And modified input is another defense. It tries to pre-process the inputs during the testing stage. And methods include data compression, foveation, and randomization. However, this approach will result in classification accuracy degradation on clean examples. And a common issue of current defenses is that they are not considering adaptive attackers, meaning that once the attackers acquire the details of the victim model and the defense mechanism, they can always design the stronger next generation adversarial attacks. And to address the shortcoming of existing approaches, in this research we consider a dynamic defense called moving target defense, or MTD. MTD is a generic idea to secure systems by making them more dynamic through changing their properties from time to time. By adding diversity and randomness to the systems, it reduces the likelihood of successful attacks by moving the system faster than the attackers can learn. So, in a word, Static defense grants the advantage of time to attackers, and MTD revokes that advantage. Here I take the example of the visual sensing of a car to give a preview of our approach. So when a car is being manufactured, it is deployed with a factory model for visual sensing. Some adversary may manage to steal that factory model. For example, it may extract the memory of the car and use it to generate some adversarial example that is effective for all the cars using the same factory model. However, under our strategy of MTD, we generate multiple new models locally when the computing unit of a car is idle. For example, when the car is being charged at night. So it's difficult for the attackers to steal the locally new generated models because otherwise it needs to launch physical attacks on individual car to extract the memory. However, this introduces great computation overhead and is out of the scope of this study. And from this study, we find that the adversarial example constructed using the factory model is invalid against the new generated models. And most of them will output the correct labels. So we can use the consistency-based attack detection and the majority-based attack thwarting. And next, I'll present the system design and evaluation of our approach. We use 3 datasets, MNIST, CIFAR-10, and GTS-RB. MNIST is a 10 class of handwritten digit, and CIFAR-10 is a 10 class of different objects. And the German traffic sign recognition benchmark, or GTS-RB, has 43 classes of traffic signs. And we construct the deep models that can achieve state-of-the-art accuracy for the 3 datasets. For example, this CNN can achieve a training and validation accuracy of over 99% and over 96% on the GTS-RB dataset. And we use CNW attack to build effective white box adversarial examples. White box means when the attackers are constructing adversarial example, they require the complete knowledge of the model internals. For example, this is a clean example from the GTS-RB dataset. And pictures shown on this row are the adversarial example constructed using the CNW attack. We can see that they are visually the same as the clean example. However, if we ask the CNN shown above to make classification, it will make mistake. For example, the last speed limit sign would be misclassified to a stop sign. And we conduct extensive measurement study to understand the response of multiple new models to the adversarial examples. And the first observation is that adversarial example has transferability to new models. We construct 20 new models and use them to classify a single adversarial example. The ground truth label is 1 and the target label is 0. And this pie diagram shows the distribution of the 20 new models output. We can see there are 3 output class labels, 1, 5, and 9. And 85% of the models will output the correct class label, that is 1, and 15% of the new models will output the wrong labels. So in this case, we can use the majority vote to give the correct output. And from a more extensive test, we find that adversarial example can mislead the new models with a probability from 7 to 17%. So using a single new model may not thwart adversarial examples completely, and we'd better use multiple new models. This figure shows the distribution of the number of distinct outputs of 20 new models when we test them using many adversarial examples. and the probability that the 20 new model outputting non-identical result is 51%, meaning that we can use consistency check to detect half of the adversarial examples. And the probability that all the model outputting the same result is 49%, meaning that the consistency check cannot detect the adversarial example. However, in this case, almost all the new adversarial example will fail to mislead the new model, meaning that all the new model will output the correct label. So we can use majority vote to give classification. And the second challenge is the retraining overhead of new model. So we design a retrain mechanism. We add perturbations to a well-trained base model and use that as the starting point of our retrain process. This figure shows the number of epochs for new model retraining. And the bars from the top shows the result obtained from retraining new models from scratch. And different colors represent different data set. And we also add different level of perturbation to the base model. And this figure shows that our retraining mechanism can greatly reduce the retrain computation overhead. And this slide shows the result when there is no attack. When there is attack. This figure shows the successful defense rate or security versus the number of new models in auto mode. And different lines represent different level of perturbation added to the base model. We can see that in general, the security increased with the number of new models as well as the level of perturbation. So there's a trade-off between the computation overhead and the security. And when we consider human in the loop, there is a general trade-off between the false positive and true positive rate. Because we consider human to be immune to adversarial examples, so when true positive, human can help correct the adversarial example, so the security will be improved. However, a higher true positive rate also means a higher false positive rate. And a higher false positive rate will incur unnecessary human classification on clean example. So this is a trade-off between the security improvement and the overhead incurred to human. And in the next section, I'll present the implementation of our system. We deploy the new models on 2 embedded computing boards, an NVIDIA Jetson AGX and an NVIDIA Jetson Nano, to investigate the runtime overhead of our approach. And Nano is a lower-end platform compared with the AGX. So to classify images using multiple models, we may have 2 schemes, parallel or serial. And parallel executes multiple models at the same time, and serial executes model one by one. In our experiment, we test both schemes on the computing boards using Keras, and we find that the parallel DeepMTD only brings around 20% improvement in the inference time. However, the serial implementation can well support an early stopping mechanism. Early stopping means we execute the models one by one, and once we accumulate enough confidence about the input, we stop and make decisions. And now so the serial may reduce the inference time and as well as the computation overhead. And now I'll detail this early stopping mechanism. Given a set of new models and an input, first we randomly select 3 models from these new models. And we keep adding new models to make classification until the consistency of this new model's output is larger than a threshold. And we will consider this input to be a clean example. However, if all the models are used and the consistency is still lower than the threshold, we will think it is an adversarial example. And we conduct extensive evaluation on the performance of serial DeepMTD with early stopping. And this figure shows the number of models used versus the consistency threshold when there's no attack. And the whisker represent minimum and maximum. The red dots are the average. We can see that when there's no attack, the serial DeepMTD can significantly reduce the number of used models. Because when the input is a clean example, all the model tends to output the same correct labels. And when there's attack, we can see that even under the most stringent consistency threshold of 100%, the number of used models can still be reduced to around 12 on average. And since adversarial example is a rare event, so the serial DeepMTD can greatly reduce the number of used models during runtime. And also, we show that the serial DeepMTD will only have slight performance compromise. And details can be found in our paper. And this is the conclusion of this work. Thank you for listening.